Learning objectives. In this chapter, the user would learn the following in detail: discrete distributions, binomial, Poisson, geometric, continuous distributions, uniform, exponential, normal and gamma, moments of these distributions, central limit theorem and its applications. Central limit theorem and uses. In the discussion leading to the law of large numbers, we saw visually that the sample means from a sequence of independent random variables converge to their common distributional mean as the number of random variables increases. In symbols, xn bar tends to mu as n tends to infinity. Using the Pythagorean theorem, for independent random variables, we obtained the more precise statement that the standard deviation of xn is inversely proportional to square root of n, the square root of the number of observations. For example, for simulations based on observations of independent random variables uniformly distributed 0, 1, we see, as anticipated, the running averages converging to the distributional mean, mu equal to integral 0 to 1 x into f of x dx equal to integral 0 to 1 x dx equal to x squared by 2 with limits 0 to 1 equal to, the answer is 1 by 2. Now we zoom around the mean value of mu equal to 1 by 2 because the standard deviation sigma xn alpha 1 by square root of n. We magnify the difference between the running average and the mean by a factor of Pn and investigate the graph of versus n. Square root of n into 1 by n Sn minus mu. The results of a simulation are displayed in here as follows. Running average of independent random variables uniform on 0, 1, running average centered at the mean value of 1 by 2 and the magnified by n. As we see here, even if we extend this simulation for larger values of n, we continue to see fluctuations about the center of roughly the same size, and the size of the fluctuations for a single realization of a simulation cannot be predicted in advance. Thus, we focus on addressing a broader question. Does the distribution of the size of these fluctuations have any regular and predictable structure? This question and investigation that led to its answer, the central limit theorem, constitute one of the most important episodes in mathematics. Let's begin by examining the distribution for the sum of x1, x2, etc. xn, independent and identically distributed random variables. What distribution do we see? Let's look first to the simplest case, xi, Bernoulli random variables. In this case, the sum Sn is a binomial random variable, so we examine two cases. In the first step, we keep the number of trials in the same at n is equal to 100 and vary the success probability p. In the second case, we keep the success probability the same at p is equal to 1 by 2 but vary the number of trials. The curves look like bell curves. The center and spread vary in ways that are predictable. The binomial random variable Sn has mean np and standard deviation square root of np into 1 minus p. Success in 100 Bernoulli trials with p equal to 0.2, 0.4, 0.6 and 0.8. Success in Bernoulli trials with p equal to 1 by 2 and n is equal to 20, 40 and 80. Thus, if we take the standardized version of the sums of Bernoulli random variables, Zn is equal to Sn minus np divided by square root of np into 1 minus p. Then, these bell curve graphs would lie on the top of each other. For our next example, we look at the density of the sum of standardized exponential random variables. The exponential density is strongly skewed, and so we have to wait for larger values of n before we see the bell curve merge. In order to make comparisons, we examine standardized versions of the random variables with mean, mu, and variance sigma square. To accomplish this, we can either standardize using the sum Sn having mean n mu and standard deviation sigma square root of n, or we can standardize using the sample mean xn having mean mu and standard deviation sigma by square root of n. This yields two equivalent versions of the z score. Zn is equal to Sn minus n mu divided by sigma into square root of n equal to xn bar minus mu divided by sigma by square root of n equal to square root of n by sigma into xn bar minus mu. We see the densities approaching that of the bell curve for a standard normal random variables. Even for the case of n equal to 32, we see a small amount of skewness, that is a remnant of the skewness in the exponential density. The theoretical result behind these numerical explorations is called the classical central limit theorem. Displaying the central limit theorem graphically, the density of standardized version of the sum of n independent exponential random variables for n is equal to 2, dark blue, 4, green, 8, red, 16, light blue, and 32, magenta. Limit n tends to infinity. F Zn of z equal to limit n tends to infinity, probability of Zn less than or equal to z equal to 1 by square root of 2 pi integral minus infinity to z e power minus z square by 2 dx equal to pi of z. In practical terms, the central limit theorem states that probability of a less than Zn less than or equal to b approximately equal to probability of a less than z less than or equal to b equal to pi of b minus pi of a. This theorem is an enormously useful tool in providing good estimates for probabilities of events depending on either Sn or Xn. Delta method. Let's use repeated independent measurements y1, y2, etc. yn to estimate a quantity q by its sample mean y bar. If each measurement has mean mu square y and variance sigma square y, then y bar as mean q is equal to mu y and variance sigma square y by n. By the central limit theorem, Zn equal to y bar minus mu y divided by sigma y divided by square root of n. As a distribution that can be approximated by a standard normal, we can apply the propagation of error analysis based on a linear approximation of g of y bar to obtain g of y bar approximately equal to g of mu y and variance g of y bar approximately equal to g dash of mu y whole square sigma square y divided by n. Thus, the reduction in the variance in the estimate of q propagates to a reduction in variance in the estimate of g of q. However, the central limit theorem gives us some additional information returning to the linear approximation. G of y bar approximately g of mu y plus g dash of mu y into y bar minus mu y. The central limit theorem tells us that y bar has a nearly normal distribution, thus the linear approximation to g of y bar also has nearly a normal distribution, moreover with repeated measurements. The variance of y bar is the variance of a single measurement divided by n. As a consequence, the linear approximation under repeated measurements yields a better approximation because the reduction in variance implies that the difference y bar minus mu y is more likely to be small. The delta method combines the central limit theorem and the propagation of error. G of y bar minus g of mu y divided by sigma g of y bar approximately equal to g dash of mu y into y bar minus mu y divided by g dash of mu y divide sigma y by square root of n equal to plus or minus zn. The last equality uses brackets. The plus or minus sign depends on the sign of the derivative g dash of mu y. Because the negative of standard normal is also a standard normal, we have the desired approximation to the standard normal. Then Zn converges in distribution to a standard normal random variable. In this way, the delta method greatly extends the applicability of the central limit theorem. We will now move to a fundamental issue in statistic estimation. The analysis of the properties an estimate are, namely, its accuracy and its precision, are based to a large extent on the tools in probability theory that we have developed here: the law of large numbers, the central limit theorem, and their extensions. We finish the discussion on the central limit theorem with a summary of some of its applications. Summary of normal approximations. The standardized score or z-score of some random quantity is z is equal to random quantity minus mean divided by standard deviation. The central limit theorem and extensions like the delta method tells us when the z-score has an approximately standard normal distribution. Thus, using R, we can find good approximations by computing the probabilities of probability of z less than z, probability of normal of z, and probability of z greater than z using 1 minus probability of normal of z or probability of z1 less than z less than z2 using the difference probability of normal of z2 minus probability of normal of z1. The density function for Sn for a random sample of size n equal to 10, red, 20 green, 30 blue, and 40 purple. In this example, the observations are normally distributed with the mean mu equal to 1 and standard deviation sigma equal to 10. Sample sum. If we have a sum Sn of n independent random variables x1, x2, etc. xn whose common distribution as mean mu and variance sigma square, then the mean expectation of Sn is equal to n mu. The variance of Sn equal to n sigma square. The standard deviation is sigma square root of n. Thus, Sn is approximately normal with mean n mu and variance n sigma square. The z-score in this case is Zn equal to Sn minus n mu divided by sigma into square root of n. We can approximate probability of Zn less than x by noting that this is the same as computing and finding probability of Zn less than z using the standard normal distribution. Zn equal to Sn minus n mu divided by sigma into square root of n less than x minus n mu divided by sigma into square root of n equal to z. For a sample mean, x bar equal to x1 plus x2 plus etc. at the end xn divided by n. The mean expectation of x bar is equal to mu. The variance of x bar equal to sigma square by n. The standard deviation is sigma by square root of n. Thus, x bar is approximately normal with the mean mu and variance sigma square by n. The z-score in this case is Zn equal to x bar minus mu divided by sigma by square root of n. Thus, x bar less than x is equivalent to Zn equal to x bar minus mu divided by sigma by square root of n less than x minus mu by sigma by square root of n. For Bernoulli trials x1, x2, etc. xn, with success probability P, let P hat equal to x1 plus x2 etc. plus xn divided by n be the sample proportion, then the mean expectation of P hat equal to P, the variance of P hat equal to P into 1 minus P divided by n. The standard deviation is square root of P into 1 minus P divided by n. Thus, P hat is approximately normal with a mean P and variance P into 1 minus P divided by n. The z-score in this case is Zn equal to P hat minus P divided by square root of P into 1 minus P divided by n. For the special case of Bernoulli trials, normal approximations often use a continuity correction. Exponential distribution. F of x comma lambda equal to lambda e power minus lambda x. Exponential distribution is the probability distribution that describes the time between events in a Poisson process, that is, a process in which events occur continuously and independently at a constant average rate. Geometric distribution. It is the continuous analog of the geometric distribution and it has a key property of being memoryless. Poisson distribution. In addition to being used for the analysis of Poisson process, it is found in various other contexts. Exponential distribution. Note that the exponential distribution is not the same as the class of exponential families of distributions, which is a large class of probability distributions that includes the exponential distribution as one of its members, but also includes the normal distribution, binomial distribution, gamma distribution, Poisson, and many others. Probability density function. The probability density function of an exponential distribution is f of x comma lambda equal to lambda e power minus lambda x, x greater than or equal to 0, then 0, x less than 0. Alternatively, this can be defined using the Heaviside step function h of x. F of x comma lambda equal to lambda e power minus lambda x h of x. Here, lambda greater than 0 is the parameter of the distribution, often called the rate parameter. The distribution is supported on the interval 0, infinity, where 0, infinity in open interval, 0, infinity in closed interval, 0, infinity in closed interval, and also at the same time in the same we using the open interval. If a random variable x as this distribution, we write x follows expectation of lambda. The exponential distribution exhibits infinite divisibility. Cumulative distribution function. The cumulative distribution function is given by f of x comma lambda equal to 1 minus e power minus lambda x, x greater than or equal to 0, where 0, x less than 0. Alternatively, this can be defined using the Heaviside step function h of x. F of x comma lambda equal to 1 minus e power minus lambda x into h of x. Alternative parametrization. A commonly used alternative parametrization is to define the probability density function of an exponential distribution as where beta greater than 0 is a scale parameter of the distribution and is the reciprocal of the rate parameter, lambda defined above. In the specification, beta is a survival parameter in the sense that if a random variable x is the duration of time that a given biological or mechanical system manages to survive, and x follows exponential of beta, then e of x equal to beta. That is to say, the expected duration of survival of the system is beta units of time. The parametrization involving the rate parameter arises in the context of events arriving at the rate lambda when the time between events, which might be modeled using an exponential distribution, as a mean of beta equal to lambda inverse. The alternative specification is sometimes more convenient than the one given above, and some authors will use it as a standard definition. This alternative specification is not used here. Unfortunately, this gives rise to a notational ambiguity. In general, the reader must check which of these two specifications is being used if any author writes x follows exponential of beta, since either the notation in the previous using lambda or the notation in this section here using beta to avoid confusion could be intended. Mean, variance, moments and median. The mean or expected value of an exponentially distributed random variable x with rate parameter lambda is given by expectation of x equal to 1 by lambda. In light of the examples given above, this makes sense. If you receive phone calls at an average rate of 2 per hour, then you can expect to wait half an hour for every call. Mean, variance, moments and median. The variance of x is given by variance of x equal to 1 by lambda square. The moments of x for n equal to 1, 2, etc. are given by expectation of x power n equal to n factorial divided by lambda power n. The median of x is given by m of x equal to ln of 2 divided by lambda less than expectation of x. Memorylessness. An exponentially distributed random variable t obeys the relation probability of t greater than s plus t divided by t greater than s equal to probability of t greater than t for every s comma t greater than or equal to 0 when t is interpreted as the waiting time for an event to occur relative to some initial time. This relation implies that if t is conditioned on a failure to observe the event over some initial period of time s, the distribution of the remaining waiting time is the same as the original unconditional distribution. Quantiles. The quantile function, inverse cumulative distribution function for expectation of lambda is f inverse of p comma lambda equal to minus ln of 1 minus p divided by lambda, where 0 less than or equal to p less than 1. Gamma distribution. In this section, we will study a family of distributions that have special importance in probability statistics. In particular, the arrival time in the Poisson process have gamma distributions, and the chi-square distribution is a special case of the gamma distribution. The gamma function. The gamma function was first introduced by Leonhard Euler. The gamma function is defined as follows. Integral 0 to infinity x power k minus 1 e power minus x dx equal to integral 0 to 1 x power k minus 1 e power minus x dx plus integral 1 to infinity x power k minus 1 e power minus x dx. For the first integral 0 to 1 x power k minus 1 e power minus x dx less than or equal to integral 0 to 1 x power k minus 1 dx equal to 1 by k. For the second integral, let n equal to k, then integral 0 to infinity x power k minus 1 e power minus x dx less than or equal to integral 0 to infinity x power n minus 1 e power minus x dx. The last integral can be evaluated explicitly by integrating by parts and is finite for every n belongs to n plus. Finally, if k less than or equal to 0, note that integral 0 to 1 x power k minus 1 e power minus x dx less than or equal to e power minus 1 integral 0 to 1 x power k minus 1 dx equal to infinity. The lower incomplete gamma function is defined by gamma of k comma x equal to integral 0 to x t power k minus 1 e power minus t dt, where k comma x belongs to 0 comma infinity. Stirling's formula. One of the most famous asymptotic formulas is Stirling's formula, named for James Stirling. Gamma x plus 1 approximately equal to x by e whole power x square root of 2 pi x as x tends to infinity. As a special case, Stirling's result gives an asymptotic formula for the factorial function n factorial approximately equal to n by e whole power n square root of 2 pi n as n tends to infinity. Standard gamma distribution. A random variable x has a standard gamma distribution with shape parameter k belongs to 0, infinity if it has the probability density function f given by f of x equal to 1 by gamma k x power k minus 1 e power minus x, where 0 less than x less than infinity. Clearly, f is a valid probability density function since f of x greater than 0 for x greater than 0, and by definition gamma k is the normalizing constant for the function. X tends to x power k minus 1 e power minus x on 0, infinity. Thus, the gamma distribution is a continuous distribution on 0, infinity. The following theorem shows that the gamma density has a rich variety of shapes and shows why k is called the shape parameter. The gamma probability density function satisfies the following properties. If 0 less than k less than 1, f is decreasing with f of x tends to infinity as x decreasing 0. If k equal to 1, f is decreasing with f of 0 equal to 1. If k greater than 1, f increases, then decreases with mode at k minus 1. If 0 less than k less than or equal to 1, f is concave upward. If 1 less than k less than or equal to 2, f is concave downward, then upward, with inflection point at k minus 1 plus square root of k minus 1. If k greater than 2, f is concave upward, then downward, then upward, again with inflection points at k minus 1 plus or minus square root of k minus 1. These results follows from standard calculus for x greater than 0. F dash of x minus 1 by gamma k x power k minus 2 e power minus x k minus 1 minus x. F double dash of x equal to 1 by gamma k x power k minus 3 e power x k minus 1 k minus 2 minus 2 into k minus 1 into x plus x square. The special case k equal to 1 gives a standard exponential distribution. When k greater than or equal to 1, the distribution is unimodal. Special distribution simulator. In the simulation of the special distribution simulator, select the gamma distribution, vary the shape parameter and note the shape of the density function. For various values of k, run the simulation 1000 times and compare the empirical density function to the true probability density function. The distribution function and the quantile function do not have simple, closed representations for most values of the shape parameter. However, the distribution function has a trivial representation in terms of the incomplete and complete gamma functions. The distribution function f of the standard gamma distribution with shape parameter k and is given by f of x equal to gamma of k comma x divided by gamma k, where x belongs to 0, infinity. Approximate values of the distribution and quantile functions can be obtained from special distribution calculator and from most mathematical and statistical software packages. Using the special distribution calculator, find the median, the first and third quartiles, the interquartile range in each of the following cases: k equal to 1, k is equal to 2, k equal to 3. Moments. The mean and variance of the standard gamma distribution are very simple. If x has a standard gamma distribution with shape parameter k, then expectation of x equal to k, variance of x equal to k. From the fundamental identity, expectation of x equal to integral 0 to infinity x into 1 divided by gamma k x power k minus 1 into e power x dx equal to gamma k plus 1 divided by gamma k equal to k. From the fundamental identity again, expectation of x square equal to integral 0 to infinity x square into 1 divided by gamma k x power k minus 1 e power x dx equal to gamma k plus 2 divided by gamma k equal to k plus 1 into k. Then variance of x equal to expectation of x square minus expectation of x whole square equal to k. Gamma distribution. In the simulation of the special distribution simulator, select the gamma distribution, vary the shape parameter and note the size and location of the mean plus or minus standard deviation bar. For selected values of k, run the simulation 1000 times and compare the empirical mean and standard deviation to the distribution mean and standard deviation. More generally, the moments can be expressed easily in terms of the gamma function. If x has a standard gamma distribution with shape parameter k, then expectation of x power a equal to gamma a plus k divided by gamma k if a greater than minus k. Expectation of x power n equal to k power n equal to k into k plus 1 etc. k plus n minus 1 if n belongs to n. For a greater than minus k, expectation of x power a equal to integral 0 to infinity x power a 1 divided by gamma k x power k minus 1 e power minus x dx equal to 1 divided by gamma k integral 0 to infinity x power a plus k e power minus x dx equal to gamma a plus k divided by gamma k. If n belongs to n, then by fundamental identity, gamma k plus n equal to k into k plus 1 etc. k plus n minus 1 gamma k. So, the result follows from A. Note also that expectation of x power a equal to infinity if a less than or equal to minus k. We can now also compute the skewness and the kurtosis. Moment generating function. The following theorem gives moment generating function if x has the gamma distribution with shape parameter k, then expectation of e power tx equal to 1 divided by 1 minus t whole power k, comma t less than 1. For t less than 1, expectation of e power tx equal to integral 0 to infinity e power tx into 1 divided by gamma k x power k minus 1 e power minus x dx equal to integral 0 to infinity 1 divided by gamma k x power k minus 1 e power minus x into 1 minus t dx. Substituting u equal to x into 1 minus t so that x equal to u divided by 1 minus t and dx equal to du divided by 1 minus t gives expectation of e power tx equal to 1 divided by 1 minus t whole power k integral 0 to infinity 1 divided by gamma k u power k minus 1 e power minus u du equal to 1 divided by 1 minus t whole power k. The general gamma distribution. The gamma distribution is usually generalized by adding a scale parameter. If z is the standard gamma distribution with shape parameter k and b belongs to 0, infinity, then x equal to bz as the gamma distribution with shape parameter k and scale parameter b. The reciprocal of the scale parameter or equal to 1 divided by b is known as the rate parameter, particularly in the context of the Poisson process. The gamma distribution with parameters k equal to 1 and b is called the exponential distribution with the scale parameter b or rate parameter r is equal to 1 by b. More generally, when the shape parameter k is a positive integer, the gamma distribution is known as the Erlang distribution, named for the Danish mathematician Agner Erlang. The exponential distribution governs the time between arrivals in the Poisson model, while the Erlang distribution governs the actual arrival times. Basic properties of the general gamma distribution follow easily from corresponding properties of the standard distribution and basic results. For scale transformations, distribution functions. If x has the gamma distribution with shape parameter k and scale parameter b, then x has probability density function f given by f of x equal to 1 divided by gamma k b power k x power k minus 1 e power minus x by b, x belongs to 0, infinity. Recall that if G is the PDF of the standard gamma distribution with shape parameter k given above. Then f of x equal to 1 by b g of x by b for x greater than 0. Gamma probability density function. Recall that the inclusion of a scale parameter does not change the shape of the density function but simply scales the graph horizontally and vertically. In particular, we have the same basic shapes as for the standard gamma density function. The gamma probability density function satisfies the following properties. If 0 less than k less than 1, f is decreasing with f of x tends to 0 as x decreasing to 0. If k equal to 1, if f is decreasing with f of 0 equal to 1, if k greater than 1, f increases then decreases with mode at k minus 1. If 0 less than k less than or equal to 1, f is concave upward. If 1 less than k less than or equal to 2, f is concave downward and then upward with inflection point at k minus 1 plus square root of k minus 1. If k greater than 2, f is concave upward, then downward, then upward again with inflection points at k minus 1 plus or minus square root of k minus 1. Gamma distribution. If x is a gamma distribution with shape parameter k and scale parameter b, then the distribution function f of x is given by f of x equal to gamma of k comma x by b divided by gamma k, where x belongs to 0 comma infinity. As usual, x equal to bz, where z is the standard gamma distribution with shape parameter k. Then probability of x less than or equal to x equal to probability of z less than or equal to x divided by b for x belongs to 0 comma infinity. So the result follows from the distribution function of the standard gamma distribution given above. Moments. Suppose that x has the gamma distribution with shape parameter k and scale parameter b, then expectation of x power a equal to b power a gamma a plus k divided by gamma k for a greater than minus k. Expectation of x power n equal to b power n k power n equal to b power n into k plus 1 etc. k plus n minus 1 if n belongs to n. Again, let x equal to bz, where z is the standard gamma distribution with shape parameter k. The result follow from the moment results above, since expectation of x power a equal to b power a expectation of z power a. Suppose that x is the gamma distribution with shape parameter k and scale parameter b. The moment generating function of x is given by expectation of e power tx equal to 1 divided by 1 minus bt whole power k, where t less than 1 divided by b. Let x equal to bz, where z as the standard gamma distribution with shape parameter k, then expectation of e power tx equal to expectation of e power tb into z. So the result follows from the moment generating function result above. Gamma distribution. In the special distribution simulator, select the gamma distribution for various values of the scale parameter, increase the shape parameter, and note the increasingly normal shape of the density function. For selected values of the parameters, run the experiment 1000 times and compare the empirical density function to the true probability density function. The gamma function is a member of the general exponential family of the distributions. The gamma distribution with shape parameter k and scale parameter b is a two-parameter exponential family with the natural parameters k minus 1, minus 1 divided by b and natural statistics ln of x, x. This follows from the definition of the general exponential family. The gamma probability density function can be written as f of x equal to 1 divided by b power k into gamma k exponential of k minus 1 ln of x minus 1 by b into x, where x belongs to 0, infinity. Computational exercise. Suppose that the lifetime of a device in a house has the gamma distribution with shape parameter k is equal to 4 and the scale parameter b is equal to 100. Find the probability that the device will last more than 300 hours. Find the mean and standard deviation of the lifetime. Answer. Let x denote the lifetime in hours. Probability of x greater than 300 equal to 13 into e power minus 3, approximately equal to 0.6472. Then expectation of x equal to 400, standard deviation of x equal to 200. Suppose that y has the gamma distribution with parameters k equal to 10 and b is equal to 2. For each of the following, compute the true value using the special distribution calculator and then compute the normal approximation. Compare the results. Probability of 18 less than x less than 25. B. The 80th percentile of y. Answer. Probability of 18 less than x less than 25, approximately equal to 0.4095. Y 0.8 equal to 25.038. Y 0.8 approximately equal to 25.325. Normal distribution. It is very commonly occurring continuous probability distribution, a function that tells the probability that an observation in some context will fall between any two real numbers. Normal distributions are extremely important in statistics and are often used in the natural and social sciences for real valued random variables whose distributions are not known. The normal distribution is immensely useful because of the central limit theorem, which states that under mild conditions, the mean of many random variables independently drawn from the same distribution is distributed approximately normally, irrespective of the form of the original distribution. Bell curve. The Gaussian distribution is sometimes informally called the bell curve. However, many other distributions are bell-shaped, such as Cauchy students and logistic. Gaussian bell curve. The terms Gaussian function and a Gaussian bell curve are also ambiguous because they sometimes refer to multiples of the normal distribution that cannot be directly interpreted in terms of probabilities. The density function of normal distribution is given by f of x comma mu comma sigma equal to 1 by sigma square root of 2 pi e power minus x minus mu whole square divided by 2 sigma square. Normal distribution. The density function of normal distribution is given by f of x comma mu comma sigma equal to 1 by sigma square root of 2 pi e power minus x minus mu whole square divided by 2 sigma square. The parameter mu in this definition is the mean or expectation of the distribution and also its median and mode. The parameter sigma is its standard deviation. Its variance is therefore sigma square. A random variable with a Gaussian distribution is said to be normally distributed and is called a normal deviate. If mu equal to 0 and sigma equal to 1, the distribution is called the standard normal distribution or the unit normal distribution, and a random variable with the distribution is a standard normal deviate. The normal distribution is the only absolutely continuous distribution, all of whose cumulants beyond the first two, that is, other than the mean and variance, are 0. It is also the continuous distribution with the maximum entropy for a given mean and variance. The normal distribution is subclass of the elliptical distributions. The normal distribution is symmetric about its mean and is non-zero over the entire real line. Normal distribution, as such, it may not be a suitable model for variables that are inherently positive or strongly skewed, such as the weight of a person or the price of a share. Such variables may be better described by other distributions, such as the log normal distribution or Pareto distribution. Standard normal distribution. The simplest case of a normal distribution is known as the standard normal distribution. This is a special case where mu equal to 0 and sigma equal to 1, and it is described by this probability density function pi of x equal to e power minus 1 by 2 x square divided by square root of 2 pi. The factor 1 divided by square root of 2 pi in this expression ensures that the total area under the curve pi of x is equal to 1. The 1 by 2 is the Exponent ensures that the distribution has unit variance and therefore also unit standard deviation. This function is symmetric around x equal to 0, where it attains its maximum value 1 by square root of 2 pi and has the inflection points at plus 1 and minus 1. General normal distribution. Any normal distribution is a version of the standard normal distribution whose domain has been stretched by a factor sigma, the standard deviation, and then translated by mu, the mean value. F of x comma mu comma sigma equal to 1 by sigma into pi of x minus mu by sigma. The probability density must be scaled by 1 by sigma so that the integral is still 1. It is unimodal. Its first derivative is positive for x less than mu, negative for x greater than mu, and 0 only at x equal to mu. Its density function is long concave. The Poisson distribution. Many experimental situations occur in which we observe the counts of events within a set unit of time, area, volume, length, etc. The number of cases of a disease in different towns, the number of mutations in set-sized regions of a chromosome, the number of dolphin pod sightings along a flight path through a region, the number of particles emitted by a radioactive source in a given time, the number of births per hour during a given day. The Poisson distribution. The Poisson distribution is a discrete probability distribution for the counts of events that occur randomly in a given interval of time or space. If we let x equal to the number of events in a given interval, then if the mean number of events per interval is lambda. The distribution was first introduced by Simons Denis Poisson, 1781 to 1840, and published together with his probability theory. The number of discrete occurrences, sometimes called events or arrivals, that take place during a time interval of given length. For instance, suppose someone typically gets 4 pieces of mail per day on average. There will be, however, a certain spread, sometimes a little more, sometimes a little fewer, once in a while nothing at all. Given only the average rate for a certain period of observation, pieces of mail per day, phone calls per hour, etc., and assuming that the process or mix of process that produces the event flow is essentially random, the Poisson distribution specifies how likely it is that the count will be 3 or 5 or 10 or any other number during one period of observation. That is, it predicts the degree of spread around a known average rate of occurrence. Definition. A discrete random variable x is said to have a Poisson distribution with parameter lambda greater than 0. If k equal to 0, 1, 2, etc. The probability mass function is given by f of k comma lambda equal to probability of x equal to k is equal to lambda power k e power minus lambda divided by k factorial, where e is Euler's numbers. E is equal to 2.71828. K factorial is the factorial of k. The positive real number lambda is equal to the expected value of x and also to its variance. Lambda equal to expectation of x equal to variance. The Poisson distribution can be applied to systems with a large number of possible events, each of which is rare. How many such events will occur during a fixed time interval? Under the right circumstances, this is a random number with the Poisson distribution. Mean. The expected value and variance of a Poisson distributed random variable are both equal to lambda. The coefficient of variance is lambda power minus 1 by 2, while the index of dispersion is 1. The mean absolute deviation about the mean is expectation of x minus lambda equal to 2 times of expectation of minus lambda into lambda power lambda plus 1 divided by lambda factorial. The mode of a Poisson distributed random variable with a non-integer lambda is equal to which is the largest integer less than or equal to lambda. This is also written as floor lambda, where lambda is a positive integer. The modes are lambda and lambda minus 1. All of the cumulants of the Poisson distribution are equal to the expected value lambda. The nth factorial moment of the Poisson distribution is lambda power n. Median. Bounds for the median V of the distribution are known and are sharp. Lambda minus ln 2 less than or equal to V less than lambda plus 1 by 3. Higher moments. The higher moments mk of the Poisson distribution about the origin are touch card polynomial in lambda. Mk is equal to summation I is equal to 1 to k lambda power I into ki, where the braces denote Stirling's numbers of the second kind. The coefficients of the polynomials have a combinatorial meaning. In fact, when the expected value of the Poisson distribution is 1, then Dominski's formula says that the nth moment equals the number of partitions of a set of size n, sum of Poisson distributed random variables. If xi follows Poisson distribution of lambda I is equal to 1 to etc. n are independent, and lambda is equal to summation I equal to 1 to n lambda power I, then y is equal to summation I is equal to 1 to n x power I follows Poisson distribution of lambda. Poisson as a limiting case of binomial distribution. In many binomial problems, the number of Bernoulli trials n is large, relatively speaking, and the probability of success p is small, such that np is of moderate magnitude. For example, consider problems that deal with rare events where the probability of occurrence is small. As a concrete example, counting the number of people with July 1 as birthday out of a random sample of 1000 people. It is often convenient to approximate such binomial problems using the Poisson distribution. The justification for using the Poisson approximation is that the Poisson distribution is a limiting case of the binomial distribution. Now that cheap computing power is widely available, it is quite easy to use computer or other computing devices to obtain exact binomial probabilities for experiments up to 1000 trials or more. Though the Poisson approximation may no longer be necessary for such problems, knowing how to get from binomial to Poisson is important for understanding the Poisson distribution itself. Consider a counting process that describes the occurrences of a certain type of events of interest in a unit time interval, subject to 3 simplifying assumptions discussed below. We are interested in counting the number of occurrences of the event of interest in a unit time interval. As a concrete example, consider the number of cars arriving at an observation point in a certain highway in a period of time, say 1 hour. We wish to model the probability distribution of how many cars that will arrive at the observation point in this particular highway in 1 hour. Let x be the random variable described by this probability distribution. We wish to know the probability that there are k cars arriving in 1 hour. We start with using a binomial distribution as an approximation to the probability x equal to k. We will see that upon letting n tends to infinity, the probability of x equal to k is a Poisson probability. Poisson as a limiting case of binomial distribution. Suppose that we know expectation of x is equal to alpha, perhaps an average obtained after observing cars at the observation points for many hours. The simplifying assumptions alluded to earlier are the following. Assumption 1. The number of cars arriving in non-overlapping time intervals are independent. Assumption 2. The probability of one car arriving in a very short time interval of length h is alpha h. Assumption 3. The probability of having more than one car arriving in a very short time interval is essentially 0. Assumption 1 means that a large number of cars arriving in one period does not imply fewer cars will arrive in the next period, and vice versa. In other words, the number of cars that arrive in any one given moment does not affect the number of cars that will arrive subsequently. Knowing how many cars arriving in 1 minute will not help predict the number of cars arriving at the next minute. Assumption 2 means that the rate of cars arriving is dependent only on the length of the time interval and not on when the time interval occurs. Example, not on whether it is at the beginning of the hour or towards the end of the hour. Assumption 3 allows us to think of a very short period of time as a Bernoulli trial. Thinking of the arrival of a car as a success, each short time interval will result in only one success or one failure. Assumption 2 tell us that non-overlapping short time intervals of the same length have identical probability of success overall. All three assumptions imply that non-overlapping short intervals of the same length are independent Bernoulli trials with identical probability of success, giving us the basis for applying binomial distribution. Poisson as a limiting case of binomial distribution. To start, we can break up the hour into 60 minutes into 60 Bernoulli trials. We then consider binomial distribution with n equal to 60 and p is equal to alpha by 60. So the following is an approximation to our desired probability distribution. Conceivably, there can be more than one car arriving in a minute, and observing cars in a 1 minute interval may not be a Bernoulli trial. For a 1 minute interval to qualify as a Bernoulli trial, there is either no car arriving or one car arriving in that 1 minute. So we can break up an hour into 3600 seconds into 3600 Bernoulli trials. We now consider the binomial distribution with n is equal to 3600 and p is equal to alpha by 3600. Number 2, probability of x equal to k approximately equal to 3600k, that is called 3000 ck. Alpha divided by 3600 whole power k, 1 minus alpha divided by 3600 whole power 3600 minus k, where k is equal to 0, 1, 2, etc. 3600. It is also conceivable that more than one car can arrive in 1 second, and observing cars in 1 second interval may still not qualify as a Bernoulli trial. So we need to get more granular. We can divide up the hour into n equal subintervals, each of the length equal to 1 by n. Assumption 3 ensures that each subinterval is a Bernoulli trial, either it is a success or a failure, one car arriving or no car arriving. Assumption 2 ensures that the non-overlapping subintervals all have the same probability of success. Assumption 1 let us that all the n subintervals are independent. So, breaking up the hour into n moments and counting the number of moments that are success will result in a binomial distribution with parameters n and alpha by n. So we are ready to proceed with the following approximation to our probability distribution. Probability of x equal to k. Equation 3 implies probability of x equal to k approximately equal to nck alpha by n whole power k 1 minus alpha by n whole power n minus k, where k is equal to 0, 1, 2, etc. n. As we get more granular, n tends to infinity, we show that the limit of the binomial probability in equation 3 is the Poisson distribution with parameter alpha. We show the following. Equation 4 implies probability of x equal to k equal to limit n tends to infinity nck alpha by n whole power k 1 minus alpha by n whole power n minus k equal to e power minus alpha power k divided by k factorial, where k is equal to 0, 1, 2, etc. In the derivation of equation 4, we need the following two mathematical tools. The statement 5 is one of the definition of the mathematical constant E. In the statement 6, the integer n is the numerator is greater than the integer k in the denominator. It says that whenever we work with such a ratio of two factorials, the result is the product of n with the smaller integers down to n minus k minus 1. There are exactly k terms in the product. Equation number 5, limit n tends to infinity 1 plus x by n whole power n equal to e power x. Poisson as a limiting case of binomial distribution. Equation 6 implies n factorial divided by n minus k factorial equal to n into n minus 1, n minus 2, etc. n minus k plus 1, where k less than n. The following is the derivation of 4. Equation 4 implies probability of x equal to k equal to limit n tends to infinity nck alpha by n whole power k 1 minus alpha by n whole power n minus k equal to limit n tends to infinity n factorial divided by k factorial into n minus k factorial alpha by n whole power k into 1 minus alpha by n whole power n minus k. Then limit n tends to infinity n into n minus 1, n minus 2, etc. n minus k plus 1 divided by n power k alpha power k by k factorial 1 minus alpha by n whole power n 1 minus alpha by n whole power minus k equal to alpha power k divided by k factorial. Limit n tends to infinity n into n minus 1 into n minus 2, etc. n minus k plus 1 divided by n power k into limit n tends to infinity 1 minus alpha by n whole power n into limit n tends to infinity 1 minus alpha by n whole power minus k equal to e power minus alpha power k divided by k factorial. In 7, we have limit n tends to infinity n into n minus 1 into n minus 2, etc. n minus k plus 1 divided by n power k equal to 1. The reason being that the numerator is a polynomial where the leading term is n power k. Upon dividing by n power k and taking the limit, we get 1 based on 5. We have limit n tends to infinity 1 minus alpha by n whole power n equal to e power minus alpha. For the last limit in the derivation, we have limit n tends to infinity 1 minus alpha by n whole power minus k equal to 1. We conclude with some comments. As the above derivation shows, the Poisson distribution is at heart a binomial distribution. When we divide the unit time interval into more and more subintervals, as the subintervals get more and more granular, the resulting binomial distribution behaves more and more like the Poisson distribution. The three assumptions used in the derivations are called the Poisson postulates, which are the underlying assumptions that govern a Poisson process. Such a random process describes the occurrences of the sum type of events that are of interest. Example: the arrivals of cars in our example in a fixed period of time. The positive constant alpha indicated in assumption 2 is the parameter of the Poisson process, which can be interpreted as the rate of occurrences of the event of interest, or rate of changes, or rate of arrivals in a unit time interval, meaning that the positive constant alpha is the mean number of occurrences in the unit time interval. The derivation in 7 shows that whenever a certain type of events occur according to a Poisson process with the parameter alpha, the counting variable of the number of occurrences in the unit time interval is distributed according to the Poisson distribution as indicated in 4. If we observe the occurrences of events over intervals of length other than unit length, say in an interval of length t, the counting process is governed by the same 3 postulates with the modification to assumption 2 that the rate of changes of the process is now alpha t. The mean number of occurrences in the time interval of length t is now alpha t. The assumption 2 now states that for any very short time interval of length h, and that is also a sub-interval of the interval of length t under observation, the probability of having one occurrence of event in the short interval is alpha th. Applying the same derivation, it can be shown the number of occurrences xt in a time interval of length t as the Poisson distribution with the following probability mass function. Equation 8 implies probability of xt equal to k equal to e power minus alpha t whole power k divided by k factorial, where k is equal to 0, 1, 2, etc. Uniform distribution. In probability theory and statistics, the continuous uniform distribution or rectangular distribution is a family of symmetric probability distributions, such that for each member of the family, all intervals of the same length on the distribution support are equally probable. The support is defined by the two parameters a and b, which are its minimum and maximum values. The distribution is often abbreviated u of a, b. It is the maximum entropy probability distribution for a random variate x under no constraint other than that it is contained in the distribution support. Characterization. The probability density function of the continuous uniform distribution is f of x equal to 1 divided by b minus a for a less than or equal to x less than or equal to b, 0 for x less than a for x greater than b. The values of f of x at the two boundaries a and b are usually unimportant because they do not alter the values of the integrals of f of x dx over any interval, nor of x f of x dx or any higher moment. Sometimes they are chosen to be 0 and sometimes chosen to be 1 divided by b minus a. The latter is appropriate in the context of estimation by the method of maximum likelihood. In the context of Fourier analysis, one may take the value of f of a or f of b to be 1 divided by 2 into b minus a, since then the inverse transform of many integral transforms of this uniform function will yield back the function itself, rather than a function which is equal almost everywhere, that is, except on a set of points with zero measure. Also, it is consistent with the sine function which has no such ambiguity. F of x equal to 1 divided by b minus a for a less than or equal to x less than or equal to b, 0 for x less than a or x greater than b. In terms of mean mu and variance s square, the probability density function may be written as f of x equal to 1 by 2 sigma root 3 for minus sigma root 3 less than or equal to x minus mu less than or equal to sigma root 3, then 0 otherwise. The cumulative distribution function is capital F of x equal to 0 for x less than a, x minus a divided by b minus a for a less than or equal to x less than b, 1 for x greater than or equal to b. Its inverse is f inverse of x equal to a plus x into b minus a for 0 less than x less than 1. The moment generating function is mx of t equal to expectation of e power tx equal to integral a to b e power tx into 1 divided by b minus a into dx equal to e power tb minus e power ta divided by t into b minus a, from which we may calculate the raw moments mk. Then m1 equal to integral a to b x into 1 divided by b minus a into dx equal to a plus b by 2. Then m2 is equal to integral a to b x square into 1 divided by b minus a into dx equal to a square plus ab plus b square divided by 3. Then finally mk is equal to 1 divided by k plus 1 summation I equal to 0 to k a power I equal to b power k minus I. Cumulant generating function. For n greater than or equal to 2, the n cumulant of the uniform distribution on the interval, that is closed interval 0, 1, is bn divided by n, where bn is the nth Bernoulli number. Mean expectation of x equal to a plus b by 2. Variance of x equal to a minus b whole square divided by 12. Solving these two equations for parameters a and b, given known moments expectation of x and variance of x yields a equal to expectation of x minus square root of 3 into variance of x, b is equal to expectation of x plus square root of 3 into variance of x. Substitute the values of expectation of x and variance of x, we will get a and b. Let x1, x2, etc. an be an identically independently distributed sample from uniform distribution of 0, 1. Let xk be the kth order statistic from this sample. Then the probability distribution of xk is a beta distribution of first kind with parameters k and n minus k plus 1. The expected value is expectation of xk equal to k divided by n plus 1. The variance are expectation of xk equal to k divided by n plus 1 tends to mu1 dash. Then m into m plus 1 divided by m plus n into m plus n plus 1 equal to k into k plus 1 divided by n plus 1 into n plus 2 tends to mu2 dash. Mu2 equal to mu2 dash minus mu1 dash square equal to k into k plus 1 divided by n plus 1 into n plus 2 minus k square divided by n plus 1 whole square. Then finally, variance of xk equal to k into n minus k plus 1 divided by n plus 1 whole square into n plus 2. Uniformity. The probability that a uniformly distributed random variable falls with any interval of fixed length is independent of the location of the interval itself, but it is dependent on the interval size, so long as the interval is contained in the distribution support. To see this, if x belongs to uniform distribution of a, b and in the closed interval x, x plus d is a subinterval of closed interval a, b with fixed d greater than 0. X follows uniform distribution of a, b, it having the subinterval x, x plus d. Then probability of x belongs to x plus d in the closed interval equal to integral x to x plus d dy divided by b minus a equal to d divided by b minus a, which is independent of x. This fact motivates the distribution's name. Generalization to Borel sets. This distribution can be generalized to more complicated sets than intervals. If S is a Borel set of positive finite measure, the uniform probability distribution on S can be specified by defining the PDF to be 0 outside S and constantly equal to 1 by k on S, where k is the Lebesgue measure of S. Standard uniform restricting a equal to 0 and b equal to 1, the resulting distribution u of 0, 1 is called a standard uniform distribution. One interesting property of the standard uniform distribution is that if mu1 has a standard uniform distribution, then so does 1 minus mu1. This property can be used for generating antithetic variates among other things. Related distributions. If x has a standard uniform distribution, then by the inverse transform sampling method, y is equal to minus lambda, ln of x as an exponential distribution with rate parameter lambda. If x has a standard uniform distribution, then y is equal to x power n as a beta distribution with parameters 1 by n and 1. Note, this implies the standard uniform distribution is a special case of the beta distribution with parameters 1 and 1. Then, Irwin-Hall distribution is a sum of n identically independently distributed uniform distribution of 0, 1. The sum of two independent, equally distributed uniform distributions yield a symmetric triangular distribution. Uniform distribution example. The CDF of a random variable x is given by f of x equal to 0 when x less than or equal to 0, x by 2 pi when 0 less than x less than or equal to 2 pi, 1 when x greater than 2 pi. Find the PDF of x and show that x as a uniform distribution in the interval 0, 2 pi. Find also probability of pi by 4 less than or equal to x less than or equal to pi by 2. By differentiating f of x with respect to x, obtain the PDF of x. Therefore, f of x equal to 1 divided by 2 pi for 0 less than x less than 2 pi, then 0 otherwise. Since 2 pi is constant, x is uniformly distributed over the interval 0, 2 pi. Therefore, probability of pi by 4 less than x less than pi by 2 equal to integral pi by 4 to pi by 2 1 by square root of 2 pi dx equal to 1 divided by 8. Discrete probability. The statistical or probabilistic properties of observable, either finite or countably infinite, predefined values. Unlike a continuous distribution which has an infinite number of outcomes, a discrete distribution is characterized by a limited number of possible observations. Discrete distribution is frequently used in statistical modeling and computer programming, also known as a discrete probability distribution. Binomial distribution. Introduction to binomial distribution. In probability theory and statistics, the binomial distribution is the discrete probability distribution of the number of success in a sequence of n independent yes or no experiments, each of which yields success with probability. Binomial distribution. Such a success or failure experiment is also called a Bernoulli experiment or Bernoulli trial. When n equal to 1, the binomial distribution is a Bernoulli distribution. The binomial distribution is the basis for the popular binomial test of statistical significance. The binomial distribution is frequently used to model the number of success in a sample of size n, drawn with replacement from a population of size n. If the sampling is carried out without replacement, the draws are not independent, and so the resulting distribution is a hypergeometric distribution, not a binomial one. However, for n much larger than n, the binomial distribution is a good approximation and widely used. A probability distribution that summarizes the likelihood that a value will take one of two independent values under a given set of parameters or assumptions. The underlying assumptions of the binomial distribution are that there is only one outcome for each trial, that each trial has the same probability of success, and that each trial is mutually exclusive. Assumptions for binomial distribution. For each trial, there are only two possible outcomes on each trial, S for success and F for failure. The number of trials, n, is finite. For each trial, the two outcomes are mutually exclusive. Probability of S equal to P is constant. Probability of F equal to Q equal to 1 minus P. The trials are independent. The outcome of a trial is not affected by the outcome of any other trial. The probability of success, P, is constant from trial to trial. Binomial distribution formula. P of x equal to n factorial divided by n minus x factorial into x factorial p power x into q power n minus x. N factorial. This start the count of number of ways event can occur. N minus x factorial. This stands for this ends the count of number of ways event can occur. X factorial. this deleted duplications. P power x stands for this is the probability of success for x trials. Q power n minus x stands for this is the probability of failure for the x trials. Method 1. Using the binomial probability formula for x equal to 0, 1, 2, etc. n, where n is equal to number of trials, x equal to number of success among n trials, p equal to probability of success in any one trial, q equal to probability of failure in any one trial, q equal to 1 minus p. The binomial distribution is a discrete distribution displaying data that has only two outcomes, and each trial includes replacements such as number 1. Pass or fail. Number 2. Go or not go. Number 3. Success or failure. Number 4. In or out. Number 5. Hot or cold. Number 6. Male or female. Defective, not defective. Number 8. Right-handed or left-handed. Number 9. High or low. Number 10. Heads or tails. Assumptions. Number 1. Each trial has only two outcomes. Number 2. The experiment has n identical trials. Number 3. Each trial is independent of other trials. Number 4. The probability of getting one outcome, success P, is held constant, and the probability of getting the other outcome, failure, is also held constant, 1 minus P. Number 5. Includes replacement for each trial, can be used to approximate without replacement trials, but it is suggested to use hypergeometric distribution. Let's evaluate the assumptions. A coin flip is an example of two outcomes, and each flip has the same chance for both outcomes, meaning independent. Flipping the coin n amount of times means there are n identical trials. Nothing changes from one flip to another. The odds are the same for each flip. Formula of mean, variance, standard deviation. Mean equal to mu equal to expectation of x equal to np. Variance equal to sigma square equal to np into 1 minus p. Standard deviation equal to sigma equal to square root of np into 1 minus p, where n equal to number of trials, p equal to probability of success, 1 minus p equal to probability of other outcome, failure. Formula. P of x equal to n factorial divided by n minus x factorial into x factorial, p power x, q power n minus x. The following formula is used to compute the number of experimental outcomes resulting from x success in n trials. 4 factorial equal to 4 into 3 into 2 into 1 equal to 24. The binomial distribution probability function is shown. P of x equal to n factorial divided by x factorial into n minus x factorial, p power x, q power n minus x, and x is the number of successes desired. Example 1. A manufacturing process creates 3.4% defective parts. A sample of 10 parts from the production process is selected. What is the probability that this sample contains exactly 3 defective parts? There are two outcomes, defective, not defective. Therefore, the binomial distribution equation is applied. P equal to 0.034, n equal to 10, then Q is equal to 1 minus P equal to 1 minus 0.034 equal to 0.966, that is 96.6%. Need the probability that x equal to 3. Substituting the values into the binomial probability function and solve. P of x equal to 10 factorial divided by 3 factorial into 10 minus 3 factorial, 0.034 whole cube, 0.966 whole power 7. Then P of x equal to 120 into 0.034 whole cube, 0.966 whole power 7. P of x equal to 0.003702 equal to 0.372%. Example 2. 45% of all registered voters in a national election are female. A random sample of 8 voters is selected. The probability that the sample contains 2 males is solution. 55% are male and there are 2 outcomes, male or female. N is equal to 8, P is equal to 0.55, that is called 55%. q equal to 1 minus p equal to 0.45. Need the probability that x equal to 2. P of x equal to 8 factorial divided by 2 factorial into 8 minus 2 factorial. 0.55 whole square, 0.45 whole power 6. Then P of x equal to 28 into 0.55 square, 0.45 whole power 6. Finally, the answer is P of x equal to 0.07033 equal to 7.03%. The binomial distribution model. Probability of x success equal to n factorial divided by x factorial into n minus x factorial p power x into 1 minus p whole power n minus x. Conclusion. In this chapter, we have covered the following in detail: discrete distributions, binomial, Poisson, geometric, continuous distributions, uniform, exponential, normal and gamma, moments of these distributions, central limit theorem and its applications.